Welcome to this in-depth scientific lecture on smart AI tools for microfluidics experiments. Over the next 16 minutes, we will explore how artificial intelligence is revolutionizing the way we design, execute, and analyze microfluidic experiments. Let's begin by understanding what microfluidics actually is. Microfluidics is the science and technology of systems that process or manipulate small amounts of fluids, typically in the range of microliters to picoliters, using channels with dimensions of tens to hundreds of micrometers. Imagine a chip the size of a microscope slide. Inside are tiny channels, about 100 micrometers wide, which is roughly the width of a human hair. Fluids flow through these channels, and we can control mixing, reactions, and separations at an incredibly small scale. To put this in perspective, a human hair is approximately 100 micrometers in diameter. That's the scale we're working with in microfluidic devices. Microfluidics has applications in drug discovery, clinical diagnostics, cell biology, chemical synthesis, and even environmental monitoring. The ability to work with tiny volumes saves reagents, reduces waste, and speeds up experiments. Now here's the challenge. Designing and optimizing microfluidic experiments is incredibly complex. There are thousands of parameters to consider: flow rates, channel geometries, fluid properties, temperature, mixing times, and more. A typical microfluidic experiment might have dozens of channels, multiple inlets, variable flow rates, and complex geometries. Each parameter affects the outcome. Finding the optimal combination through trial and error would take years. The parameter space is enormous. If you have 10 parameters, each with 10 possible values, that's 10 billion possible combinations to test. This is where AI comes in. Artificial intelligence, particularly machine learning, offers a solution. I can navigate this vast parameter space efficiently, learning from experiments and predicting optimal conditions. AI systems for microfluidics typically involve several components: data collection, learning algorithms, prediction models, and optimization routines. The AI observes the results of experiments, learns patterns, and suggests better parameter settings. There are three main AI approaches being used in microfluidics today. Let's examine each one in detail. The first approach is supervised learning. Here, we train an AI model on existing experimental data to predict outcomes for new conditions. Imagine we have run hundreds of experiments measuring reaction yield at different flow rates, temperatures, and reaction times. We feed this data into a neural network. The network learns the relationship between input parameters and output yield. Neural networks excel at capturing complex, nonlinear relationships that would be difficult to model with traditional equations. They can handle interactions between parameters that aren't obvious. Mathematically, the AI learns a function y equals f of x1, x2, x3, up to xn, where y is the outcome, and x values are the input parameters. Let's do a back-of-the-envelope calculation. Suppose we have 1,000 training examples and a network with 10,000 parameters. Training typically takes about 1 millisecond per example, per iteration. With 100 iterations, that's about 100 seconds or less than 2 minutes on a modern GPU. 1,000 examples times 100 iterations times 0.001 seconds equals 100 seconds. This is remarkably fast compared to running 1,000 actual physical experiments. Once trained, the model can predict outcomes for new parameter combinations in milliseconds. This allows researchers to explore thousands of virtual experiments before running any physical tests. The second approach is reinforcement learning. This is where the AI actively experiments and learns from the consequences of its actions, much like a scientist iteratively refining an experiment. In reinforcement learning, the AI agent takes an action, such as setting a flow rate. It observes the reward, which might be the reaction yield. The agent learns which actions lead to higher rewards and adjusts its strategy accordingly. Unlike supervised learning, where we need pre-existing data, reinforcement learning learns through trial and error. The AI explores the parameter space, receives feedback, and gradually homes in on optimal conditions. A concrete example is droplet generation in microfluidics. The goal might be to produce uniform droplets of a specific size. The AI adjusts flow rates and observes droplet size distribution, learning which settings produce the most uniform droplets. The AI receives high rewards when droplets are uniform and low rewards when they vary in size. Over hundreds of trials, it learns the precise combination of oil flow rate, water flow rate, and surfactant concentration that produces perfect droplets. Reinforcement learning converges much faster than exhaustive search. Instead of testing all combinations, the AI intelligently explores regions of parameter space that show promise, dramatically reducing the number of experiments needed. The third approach uses generative models to design entirely new microfluidic devices. These AI systems can propose novel channel geometries and device architectures that human designers might never consider. Generative adversarial networks, or GANs, and variational autoencoders can generate new microfluidic designs. The AI learns from existing successful designs and creates variations that optimize for specific objectives like mixing efficiency or cell sorting accuracy. What's remarkable is that AI-generated designs often include non-intuitive features that improve performance. For example, asymmetric channel widths or spiral patterns that enhance mixing in ways that wouldn't be obvious to a human designer. Let's look at a real-world example of how these AI tools are being applied. Consider high-throughput drug screening using microfluidic devices. In drug screening, we might test hundreds of compounds against various cell types. A microfluidic chip can test dozens of drugs simultaneously in separate channels. But determining optimal drug concentrations, incubation times, and cell densities is complex. An AI system can optimize multiple objectives at once, maximize the signal-to-noise ratio, minimize reagent consumption, reduce experiment time, and ensure reproducibility. These objectives often conflict, and AI helps find the best trade-offs. Let's estimate the efficiency gain. A traditional approach might require testing 100 concentration combinations for each of 20 drugs, totaling 2,000 experiments. Each experiment takes 1 day. That's over 5 years of work. 100 concentrations times 20 drugs equals 2,000 experiments. 2,000 days is 5.5 years of continuous work. With AI-guided optimization, the system might converge to optimal conditions in just 200 experiments. That's 7 months instead of 5.5 years, a factor of 10 improvement in time. The speedup is 2,000 divided by 200, which equals 10 times faster. Another powerful AI tool is computer vision for real-time analysis of microfluidic experiments. Traditional analysis requires manual observation and measurement, which is slow and subjective. Computer vision I can track individual cells or droplets in real time, measuring their size, velocity, and trajectory. Convolutional neural networks, trained on thousands of images, can identify and classify objects with superhuman accuracy. Modern convolutional neural networks can process high-speed microscopy images at 60 frames per second or faster, providing instant feedback on experiment progress. A practical application is cell sorting. The AI analyzes cell morphology in real time and triggers actuators to divert specific cells into collection channels. This enables sorting based on subtle features that would be impossible to detect manually. The AI can distinguish healthy cells from abnormal ones, or identify cells in different stages of division, all in just 5 milliseconds per cell. This enables processing thousands of cells per hour with high accuracy. The real power emerges when we integrate AI with full lab automation. This creates closed-loop systems where AI designs experiments, robots execute them, sensors collect data, and AI analyzes results to design the next experiment. Imagine a system where the AI decides which experiment to run next. A robot arm sets up the microfluidic chip, cameras monitor the experiment, and the AI analyzes the results. This cycle repeats autonomously, running experiments 24/7. These self-driving labs can operate continuously without human intervention. While a human researcher sleeps, the AI might run 50 experiments, analyze the data, and have new insights ready by morning. Let's calculate the productivity gain. A human researcher might run 5 experiments per day. A self-driving lab running continuously could perform 1 experiment every 30 minutes. That's 48 per day. 24 hours times 60 minutes divided by 30 minutes per experiment equals 48 experiments per day. 48 divided by 5 equals 9.6 times the productivity of a human researcher working normal hours. A critical consideration is data management. AI systems are only as good as the data they're trained on. Microfluidics generates enormous amounts of data: images, videos, sensor readings, and metadata. A high-throughput system might generate 10 terabytes of raw data per day. AI preprocessing reduces this to 500 gigabytes of processed features and labels that are actually used for training. The compression ratio of 20:1 is typical. Raw images are compressed, features are extracted, and only the relevant information is retained for training. It's crucial to understand that data quality matters more than quantity. 1,000 high-quality, well-labeled examples are worth more than 10,000 noisy, poorly annotated ones. Despite the tremendous potential, there are significant challenges and limitations to AI and microfluidics that we must address honestly. First is reproducibility. Microfluidic experiments can be sensitive to environmental conditions, fabrication variations, and subtle differences in materials. AI trained on one lab's data may not transfer well to another lab's setup. An AI achieving 95% accuracy in Lab A might only achieve 65% in Lab B due to equipment differences. Transfer learning techniques can help, but this remains a significant challenge. Second is interpretability. Neural networks are often black boxes. They can predict outcomes accurately, but it's difficult to understand why they make certain predictions or what physical principles they've learned. For scientific research, understanding the underlying mechanisms is as important as making accurate predictions. We need explainable AI techniques that can provide insights into the physical processes. Third is data efficiency. Training robust AI models typically requires thousands of examples. But in some microfluidic applications, each experiment is expensive or time-consuming, limiting the available training data. Emerging techniques like few-shot learning and transfer learning can help. I learn from fewer examples by leveraging knowledge from related tasks. This is an active area of research. Looking to the future, one exciting direction is physics-informed neural networks, which combine AI with physical laws and equations. Instead of learning purely from data, physics-informed neural networks incorporate known physical laws, like the Navier-Stokes equations for fluid flow. This makes them more data efficient and interpretable. For incompressible flow, the continuity equation states that the divergence of velocity equals 0. I must respect this constraint. The momentum equation relates fluid density, acceleration, pressure gradient, and viscosity. By encoding these equations into the neural network architecture, we ensure the AI predictions obey physical laws. Physics-informed AI generalizes better to new conditions because it has built-in knowledge of how fluids behave. It needs fewer training examples and is less likely to make physically impossible predictions. For researchers looking to implement AI in their microfluidics labs, there are several practical considerations. Start with a simple problem, like optimizing a single parameter such as flow rate. Don't try to tackle a complex multi-parameter optimization on your first project. Invest in robust data collection infrastructure. Automated sensors, high-quality cameras, and proper metadata tracking are essential. Garbage in, garbage out applies to AI just as much as any analysis. Use existing machine learning frameworks like TensorFlow, PyTorch, or scikit-learn rather than building from scratch. These tools have been extensively tested and optimized. Collaborate with AI experts or data scientists. Microfluidics researchers bring domain expertise, while AI specialists bring algorithmic knowledge. The best results come from interdisciplinary teams. Let's do a cost-benefit analysis for implementing AI in a microfluidics lab. Initial investment might be around $50,000 for computing hardware, software licenses, and training. Annual operating costs might be $10,000 for cloud computing, maintenance, and data storage. If the AI saves 500 hours of researcher time per year by automating optimization and analysis, and a researcher's time is valued at $50 per hour, that's $25,000 in annual savings. 500 hours times $50 per hour equals $25,000 per year. The payback period is 50,000 divided by the difference between 25,000 and 10,000, which is 3.3 years. After that, it's pure savings. Plus, the intangible benefits of improved experiment quality, faster discoveries, and competitive advantage make the investment even more attractive. Let me present a detailed case study. A pharmaceutical company wanted to optimize the synthesis of a complex organic molecule in a microfluidic reactor. Two reactants, A and B, combine in the presence of a catalyst to form the desired product. The challenge was to find optimal temperature, flow rates for each reactant, and catalyst concentration to maximize yield while minimizing byproducts. The parameter space included 4 variables: temperature from 20 to 80 degrees, 2 flow rates from 10 to 100 microliters per minute, and catalyst concentration from 0.1 to 5%. Testing all combinations would require thousands of experiments. Previous manual optimization had taken 6 months and achieved 72% yield. The goal was to improve both the yield and the timeline using AI. The team implemented a Bayesian optimization algorithm. This technique builds a probabilistic model of the objective function and intelligently selects which experiments to run next to maximize information gain. The graph shows how yield improved with each experiment. After just 42 experiments over 3 weeks, the AI found conditions achieving 87% yield, a significant improvement over the manual approach. 87% yield in 3 weeks compared to 72% in 6 months. That's a 15% improvement in yield and 8 times faster optimization. Interestingly, the optimal conditions discovered by the AI were unexpected. The temperature was lower than anticipated, but a specific ratio of flow rates created turbulent mixing that enhanced the reaction. Before we conclude, we must discuss ethical and safety considerations when deploying AI in laboratory settings. Autonomous systems must have fail-safes and emergency stop mechanisms. Humans should always be able to override AI decisions, especially when dealing with hazardous materials. Data privacy is critical. Experimental data may contain proprietary information or sensitive patient data. Secure data storage and access controls are essential. AI systems can perpetuate biases present in training data. If training data comes only from certain experimental conditions or materials, the AI may not generalize well to other scenarios. All AI predictions should be validated experimentally before being trusted for critical applications. The AI is a tool to augment human judgment, not replace it entirely. Let's wrap up with the key takeaways from this lecture. AI tools dramatically accelerate microfluidics research by efficiently exploring vast parameter spaces, optimizing complex experiments, and providing real-time analysis. We discussed 3 main AI approaches: supervised learning for prediction, reinforcement learning for optimization, and generative models for design. Integration with lab automation creates self-driving labs that operate continuously, potentially increasing productivity by 10 times or more. Challenges remain in reproducibility across different labs, interpretability of AI decisions, and data efficiency. Physics-informed AI offers promising solutions. Cost-benefit analysis shows that despite significant upfront investment, AI systems can pay for themselves within a few years through time savings and improved outcomes. Success requires interdisciplinary collaboration between microfluidics researchers, AI specialists, and automation engineers. No single expert can do it all. Looking ahead, we're moving toward democratization of AI tools for microfluidics. User-friendly software platforms are emerging that don't require deep AI expertise. Today, implementing AI requires specialists in custom code, creating a high barrier to entry. In the future, graphical user interfaces and automated pipelines will make AI accessible to all researchers. Cloud-based platforms will reduce infrastructure costs. Instead of buying expensive GPU servers, researchers can rent computing power on demand, paying only for what they use. Standardized protocols and data formats are emerging, improving reproducibility and enabling AI models trained in one lab to be easily transferred to another. In conclusion, AI is not just a buzzword in microfluidics. It's a transformative technology that's already delivering real results in drug discovery, diagnostics, and fundamental research. For researchers in this field, the question is not if you should adopt AI tools, but when and how. Starting with small pilot projects, is a low-risk way to gain experience. Remember that AI is a tool that augments human creativity and intuition. It handles tedious optimization and data analysis, freeing researchers to focus on hypothesis generation and experimental design. We're at the beginning of an exciting revolution, where AI and microfluidics converge to accelerate scientific discovery. The next decade will bring innovations we can barely imagine today. Thank you for your attention during this lecture. I hope you now have a comprehensive understanding of how smart AI tools are transforming microfluidics experiments, the underlying principles, practical implementations, and future directions. I encourage you to explore these technologies in your own research.